Okay, welcome to lecture here. We're continuing in chapter 8. Okay, so we're talking about chapter 8, and we've been talking about kind of moles and Avogadro's number, molar mass, and all those things. So we talked about sort of atomic mass, which again is what we find on the periodic table. It is that number that comes underneath the symbol, and we can use it as sort of AMU per atom. We also maybe jumped a little ahead, but we talked about it in terms of molar mass as well. So when we use something like the molar mass from the periodic table, that is basically grams per mole. And that also is the number that we see on the bottom of the symbol. Numerically speaking, grams per mole and AMU per atoms, like we talked about last time, are basically the same. And really, molar mass is our conversion factor to go from grams to moles, or moles to grams. So that's a really important sort of conversion factor that's used. We also saw Avogadro's number, and Avogadro's number is 1 mole of anything is basically 6.022 times 10 to the 23. These could be atoms in terms of the units. They could also be molecules if you're dealing with molecules. They really can be sort of any unit you want, but obviously atoms and molecules are the two sort of common units that we use here in chemistry. And really, you could think of Avogadro's number really again as really a conversion factor. And it's the conversion factor that allows you to go from moles to atoms, or moles to molecules, and vice versa backwards. So molecules to moles, or atoms to moles. So that's also sort of the key to when you want to sort of use Avogadro's number. Is it does need to mention something like that, like you need to have a number that's given to you in atoms, molecules, something like that, or you need to be looking for some type of number that ends in sort of atoms, molecules, or particles. Again, if nothing is sort of mentioned about molecules or atoms, you probably should not be using Avogadro's number in that calculation. Also, a reminder that when you do see MOL like this, that is the abbreviation for mole and not molecules. So again, the abbreviation for mole is at MOL. And again, a very common mistake people make is they see that MOL and they think kind of molecules in that particular case. And we saw that basically you can relate all those sort of things together. So basically we can say, as we can see here, if we had 1 mole of aluminum, it would have 6.022 times 10 to 23 atoms of aluminum, and it would equal 1 mole, 26.98 grams, which is that number again that we get off of the periodic table. And same thing with all these guys here. I think we also talked about at the end as well that, you know, you could do it for sort of substances as well. Something like water, for example. We could say in 1 mole of water, there would be 6.022 times 10 to 23. These would be molecules in the case of water. And in the case of water, if we needed to figure out how many grams that would be, we would go to the periodic table, and it would be 2 times the 1.008 for the 2 hydrogens, plus the 16 grams per mole for the 1 oxygen. That gives us 18.02 grams per mole would be the molar mass. So in 1 mole of water, there would be 18.02 grams, basically. So we could kind of relate these things to just elements by themselves. We could also relate these things to you know, substances, molecules, whatever it may be, and it's sort of that relationship. And really all these things essentially are really just conversion factors to really convert units. And we do use that molar mass a lot to do that grams to mole conversion. That is a very, very common conversion there that we do a lot. Any questions on any of that stuff we were talking about, I think, last time? Okay. Let's see here. I'm going to skip this one, I think. So again, here is that sort of decision sort of tree there. And again, Avogadro's number for doing something with atoms or molecules, no mention of that, probably going with molar mass. And as you can see, kind of the moles is the one that ties both of those things together. And a lot of calculations in chemistry involve getting things into that unit of moles. And from that unit of moles, you have a lot of sort of ways that you could kind of go in different directions. So if we take a look at, for example, this here, we want to determine the number of copper atoms there are in 0.35 moles of copper. So when we look at this sort of problem, there's a couple of sort of key sort of words that help us understand what we should be maybe using. And the first one is atoms here. So we're looking for atoms. So that means we do need to use Avogadro's number there somewhere along the way. We're already in 0.35 moles. So in terms of Avogadro's number, we know that 1 mole of copper in this case would equal 6.022 times 10 to the 23 atoms of copper. And again, as we talked about last time, you could really write 2 conversion factors for that. Again, you could use the atoms up on top and the moles on the bottom. Or you could flip it around and put a mole of copper up on top and the Avogadro's number there on the bottom. And you kind of treat it like a conversion factor, sort of opposites, right, will cancel. So since we're starting with moles, we would want to use sort of the conversion factor like we have here on the left, where moles are on the bottom so that they do cancel each other out. And if we sort of follow that calculation then and set it up here, we would start with our moles of copper and Avogadro's number up on top, 1 mole on the bottom. Again, here, the moles of copper are going to cancel each other out. That's going to leave us with atoms. And it looks like if you do that, you do get something like 2.11 times 10 to the 23. Also, a good reminder that you want to make sure that you do use your exponent button, especially punching in Avogadro's number. So make sure that you hit it 6.022, that EE button, EXP button, whichever sort of exponent button you have, and 23. So just like we talked about, I think earlier on in the semester, if you sort of do an Avogadro's number in some of these calculations and you find yourself sort of off, like this number is okay, but this part is not so good, it's probably the way that you're punching in sort of that exponent into your calculator. So make sure that you watch that. In terms of sort of sig figs, probably would refer back to our original number here, which has 2 sig figs. So we would probably end up with 2 significant figures in our answer. So really 2.1 times 10 to the 23 atoms of copper. Any questions on that particular one there? Okay, if we look at, again, another one here sort of involving copper, we want to determine the number of grams there are in 0.3 moles of copper. So the key on this one here is when we look at the problem here, there is no mention of atoms. There's no mention of molecules. So since we don't have any of those things, we don't need Avogadro's number in this case. So we're really going from moles to grams, and that is the molar mass from the periodic table that we get. So we would go to the periodic table again. You would look up on copper there, it would say something like 6355 underneath it. And what that number represents is in 1 mole of copper, there is 63.55 grams. And again, the molar mass basically is 63.55 grams per mole, which can be used as a conversion factor. So here we would start with moles, and we want to multiply it by the molar mass from the periodic table. That way our moles will cancel each other out. Again, here, moles are going to cancel, going to leave us with grams. We're going to multiply that across there. 0.35 times 6345, and we will end up with sure where they get that number from, but okay. 63, it should be 55, just so you know, I think. It should be 63.55 unless they change the mass a bit. Maybe they have on all these years, but it should be 63.55. And we get something like 22.2 grams. Hopefully with the right number, we still get that 22.2. So let's see, 0.35 times 63.55. Still get that number. That's good. And again here, this guy's got 2 sig figs. Probably that's the right one to look at. So we would probably want to take it to just 22 grams of copper in this particular case. Any question on those 2 calculations? Now, if we want to kind of go all the way across, for example, taking us all the way from grams, say, to atoms, we really want to put both of those sort of things together. So if we look at sort of the next example here, if we had 0.35 grams of grams of copper, how many atoms that would be? Again, here we do see atoms, which means we do need to use Avogadro's number. And remember that basically Avogadro's number is at 1 mole, 6.022 times 10 to the 23. But in order to use that, we really need to get things into moles. So we're not in moles, so we do need to use the molar mass there. So we got to first use the molar mass so that we can get the moles, and then we need to use Avogadro's number to get us to atoms. So again, a very common sort of thing that we kind of have to put all those things together to get us to what we're looking for. So here again, if we kind of look at our process, we would start with the grams and we would use the molar mass. That's good. They got the right number on this slide, so that's good. And this again comes from the periodic table. In this case, though, since we are starting with grams, we're going to use the molar mass with the grams on the bottom so that they cancel. And if you stopped right at that point, you could get an answer if you wanted to. You don't have to. You could just continue on with the calculation. If you do get an answer after the first calculation, I again would not round too much until the end. So I would take it to a good number of digits. But if you do get an answer or wherever you're at that point in the calculation, we're in units of moles. And now we can use Avogadro's number here to go from moles to atoms. Again, moles would be on top so that the moles will cancel each other and leaving us with atoms. A reminder here, math-wise, what we're doing is taking 0.35 times 1 times 6.022 times 10 to the 23. Again, I would hit equals at that point and divide it by 63.55 and hit equals. And you should get hopefully something like 3.3 times 10 to the, that should probably be 21 up on top. That's what happens when you steal the textbook, the slides, I suppose. 10 to the 21 atoms up are on top. In terms of sig figs, probably again, and like in most cases, if you kind of go with the sig figs, your original number is, you'll probably be in okay shape there. So I better check this number just to make sure. So 0.35 times 6.022 to the 23 divided by 63.55. And we do get 3.3 to the 21. And again, that should be probably your final answer in terms of sig figs, should be this guy. Any questions on those couple of examples there? Okay, so why don't you try some here, see what you come up with. So what you have next, I think, is this one. We want to know how many grams of silver are there in 1.25 moles of silver. And if you look up silver there on your periodic table, just in case you don't have one, you will find this number underneath it, 107.9. All right, so take a minute there and see what you come up with. Okay, so let's take a look here. So we want to know how many grams there are in 1.25. Again, when you see the MOL there, that is moles. So no mention of atoms, no mention of molecules. So we do not need Avogadro's number. This again is a conversion going from grams to moles. And what we use to do that is the molar mass from the periodic table. So hence the number that we got here. That means the molar mass of silver is 107.9 grams per mole that we could use as a conversion factor. We will start with the 1.25 moles of silver. Here we want to get rid of the moles and have it on the bottom. So we'll put the grams up on top. When we do the molar mass from the periodic table, we do 4 significant figures. And the number always stays with the grams, and it's always 1 mole when you take it off the periodic table. Moles here will cancel each other out, and we will end up with something like 134.875 grams. We obviously should probably clean that up a little bit here. And in terms of sig figs, again, I probably would look at this number here. This has got 4 sig figs, which should take us to right about there, which means 134.9 grams of silver. So that is, it looks like B, perhaps. Question on that calculation there. Okay, why don't you try the next one that you got, which is how many atoms are there in 1.25 grams of silver? And again, 107.9 for silver. Okay, so here we're looking for atoms. So again, that is the keyword there that you do need to use Avogadro's number along the way. Again, our 1 mole is 6.022 times 10 to the 23 atoms. Just like we talked about previously, in order to use it, it does need to be in moles, as moles is sort of that thing that ties everything together. We're in grams, so we are going to need to use the molar mass here to go from grams to moles. And then we can use, obviously, Avogadro's number there to finish up the calculation. So we'll start with the 1.25 grams of silver. We're going to use the molar mass to go from grams to moles. In this case, grams are on top, so we do want to use the grams from the molar mass on the bottom so that they cancel again in 1 mole of silver. At that point, if we stop here and get an answer, which you do not need to do, but in case you did, you would end up with something like 0.01158848. And again, I'm going to take it to a good number of digits because I'm going to continue on with the calculation at this point. So now that we have it in moles, we could use our Avogadro's number to take us from moles. Again, taking it to a good number of digits there. In this case, moles are on top, so we do want the moles on the bottom. Avogadro's number here would go up on top. And in this case, it would be atoms since we're dealing with just silver. And we would multiply it by Avogadro's number, making sure again to use our exponent button. And it looks like we do end up with something like 6.97 times 10 to the 21 atoms of silver. And that looks like perhaps D would be the right answer here. Again, in terms of the significant figures, our original number here had 3. Our final number has 3, and pretty safe bet just to follow that rule, as everything in the middle mostly will have more numbers in most cases and sort of consider conversion factors. Question on that calculation there. All right, so let's then talk about, we sort of talked a little bit about this already, but just to, again, go over it to make sure. We do want to sort of think about, does things make sense when we do these type of problems? We do want to think about the units, what way will get us there to our final sort of goal, and just really thinking about sort of Avogadro's number, molar mass as really conversion factors. So we did talk about molar mass here already. So just again, to review, we obviously can apply molar mass to formulas and substances that are not just elements by themselves. We can apply it to both ionic compounds and covalent compounds. I will say in some books, in some cases, you may sometimes hear formula mass. And formula mass is really the same thing as molar mass. And sometimes this is used for ionic compounds. We won't use it here, but occasionally you'll see that sort of name sort of pop in there. And it's basically the same thing. It's just used for ionic compounds. But as you can see here, we could do it for ionic compounds, covalent compounds. And really all we're doing is essentially going to the periodic table like we've been doing and adding up all the parts. So like we did with water here, there's 2 hydrogens, each at 1.008 grams per mole and 1 oxygen at 16. Again, giving us our molar mass for something like water of 18.02. If we had something like barium nitrate here, we have 1 barium at 137. We do need to multiply this 2 in, so that would give us 2 nitrogens, which is what this is for. And we also need to multiply that 2 into the 3, and that's how we get to the 6 oxygens, which is 16 each. Again, adding all that together gives us our molar mass for something like barium nitrate of that 261.35. Again, in most cases, people do round molar mass to 4 significant figures in most cases. We talked about this, I think, last time as well when we were talking about the experiment that we did, but hydrates do have this sort of unusual formula. It has this little dot there, and it does have some waters that are attached. So as we talked about in the experiment, a hydrate, it has really 2 parts. It has a salt part and a water part. And it's important that when you go get a molar mass of a hydrate, like we talked about last time, that you include the water in the molar mass. So as you can see here, if we were going to the periodic table, again, we would have 1 copper we would need, 1 sulfur, and 4 oxygens for the salt part. And the water part would have an additional 10 hydrogens and an additional 5 oxygens for the water part here. Again, we would need to get all those guys together, which is basically what's happened over here. And taking all those guys together again for our hydrate would give us a molar mass of 249.65. Again, it's very common that people will kind of not include the water part there when they're doing the molar mass for the hydrate. So you want to definitely make sure if it is a hydrate, you can always recognize a hydrate with this kind of weird dot sort of part that has both of these parts. And as we talked about, basically what it is, it's a solid, but when this thing crystallizes, it takes some waters with it, basically. And again, as we saw in the video, it was a solid, but it does have water sort of crystallized with it all together in this particular case. Any questions on that molar mass there that we talked about? Okay. We're going to skip this one. So why don't we kind of tie some of this stuff together, which will also answer this question here. So why don't we answer how many grams are in, let's do 32.5 moles of sodium chloride. So why don't you take a little bit here and see what you come up with, and I'll also answer this question as well in case you don't have a periodic table on you. I suppose you probably should, I imagine. This is what it looks like underneath sodium. This is what it looks like underneath chlorine. 35, 45, and 22.99 for sodium. Okay, so let's take a look. So in my made up question here, we want to know how many grams there are in 32.5 moles. So we have grams, we have moles. We don't have anything to do with atoms, molecules, or anything like that. So we really want to go from our moles to grams. Again, the molar mass is what we want to do to basically calculate that. So in this case, we have one of each, right, which is the correct formula for sodium chloride and NaCl. We would basically just add those together, and it looks like I think you get 58.44 grams per mole, which would be the actual answer to the original question, which was what is the molar mass, by taking 22.99 plus 35.45. But we're going to use this now as a conversion factor. So we have 32.5 moles of sodium chloride. Again, here we want to get rid of the moles. So we want to put the moles on the bottom. So remember, usually 4 significant figures for molar mass. Number always stays with the grams, and moles is always 1. The moles here will cancel each other out. gives us 58.44 times 32.5. And my made up number here gets us something like 1899.3 grams of sodium chloride. In terms of sig figs, again, probably would look at this number here. That is 3 significant figures. That takes us to here, which means we should round up there. And in this case, probably something like 1.90 times 10 to the 123 grams of sodium chloride would be the correct answer there in terms of sig figs. Again, if I laid up 1900, technically only has 2 significant figures with no decimal point. Decimal point has 4 significant figures. So again, only way to kind of get us to 3, a little scientific notation. Any questions on that one there? Okay, let's see here. All right, we want to know what is the molar mass of nickel 2 carbonate, but why don't we also just kind of make it a different question as well? So why don't we kind of go with how many molecules, we'll pretend that's a molecule even though it's an ionic compound. How many molecules are there in, we'll go with 12.5 grams of nickel 2 carbonate. So just in case you're not sure what the formula looks like, it looks something like that, NiCO3. And again, in case you don't have a periodic table, nickel, Nickel looks like 5869. Carbon is 1201, and oxygen is 16. All right, take a couple minutes and answer that. We're looking for how many molecules there are in 12.5 grams of nickel 2 carbonate. Okay, so let's see how we're doing here. So we want to know how many molecules, again, keyword there that our good friend Avogadro's number should be involved. Again, here we're starting with grams, so we do need to get it to that moles, which sort of ties everything together. So again, the molar mass is going to be needed to go to moles, and then we could use obviously Avogadro's number there to get us to molecules. I guess I should angle that down that way. So we'll start with the molar mass of this guy. So we have one nickel at 58.69 grams per mole. We got one carbon at 12.01 grams per mole. And we have three oxygens at 16 grams per mole. Again, adding all that together there will get us looks like 118.7 grams per mole would be our molar mass, I believe. Any questions on that part up to there? Okay. So again, for the question I asked, we're going to use that as our conversion factor. So we're first going to take the grams that it gave us. We're going to use our molar mass again as a conversion factor. Grams are up on top, so we want grams on the bottom. So again, the number stays with the grams, and it's always 1 mole. Grams will cancel. Again, you don't necessarily need to get an answer at this point. In case you did, you would have something like 0.105307. Again, taking it to a number of sig figs so I don't lose any. At this point, we now have, if I would have wrote it, moles of nickel to carbonate. We're going to use our Avogadro's number as a conversion factor. So moles are up on top, so we want the moles on the bottom. We want the 6.022 times 10 to the 23. We'll use molecules here, even though technically it's ionic. We will end up with 6.022 to the 23. Gives us something like 6.34 times 10 to the 22 molecules here of our nickel 2 carbonate. In terms of sig figs, again, defaulted really back to this number here. And that's probably good practice to do. So that's 3 sig figs. We end up with 3 sig figs. Question on any of that calculation there? Okay, then why don't you do this one? We'll actually just do what it asks. So just do the molar mass here of ammonium phosphate. Actually, we'll skip it. Let's do this one. Let's do what is the molar mass of magnesium sulfate heptahydrate? So why don't you do this guy? Magnesium sulfate heptahydrate. Let's see what you come up with. And again here, magnesium 2431, I think. And sulfur 3207, oxygen 16, and hydrogen 1.008. Should be all you need, I think. Okay, so on this one, you definitely want to start out with obviously the right formula. So hopefully remember magnesium sulfate. Magnesium is +2, sulfate's -2, should look something like this. It's a hydrate, so I'll have that little dot. And hepta prefix is 7. Hydrate is water. So we would have 7H2O in this case. So as we talked about previously, when you're dealing with a hydrate and you want the molar mass, it is everybody that is there. So that means we just need to add up all the parts there. So we got 2431 for our magnesium, plus a 3207 for our sulfur, plus 4 times 16 for our oxygen. And now it's up to you how you want to do this. You could either use the molar mass of water, which is 18.02, and take 7 times 18.02, or you could just take all the parts like we've been doing. So 14 hydrogens for the water and 7 oxygens also from the water part. Again, you could just do the 7 times 1802. So if we do all that, that is 2431 plus 3207 plus 4 times 16 plus 14 times 1.008 and a 7 times 16, and looks like perhaps 246.5 grams per mole, and looks like perhaps number A there, or letter A, would be the right one. Any questions on that there? Any questions on Avogadro's number, molar mass, going from grams to moles to atoms, molecules? Any questions on any of that stuff there? Okay, so we're going to kind of now talk about another sort of calculation that involves sort of the mass of certain compounds. And this is what is known as percent composition by mass. So if we have an actual formula, we could figure out the percent composition by mass of each of the elements that are involved. So for example, if we had iron 3 oxide and we wanted to know the percent of iron that's there, we would get first off the molar mass of the formula. So we would go to the periodic table, and again, we would add up the 2 iron masses plus the 3 oxygen masses, and that will give us our molar mass of the whole compound, and that's what would go on the bottom. On top would go just the mass of the element we're interested in, which would be the iron. So up on top we would go 2 times 5585, which is the molar mass of iron, and times it by 100 there. So up on top, the mass of just the iron in that formula, and this is the whole thing on the bottom. And again, we divide it, times it by 100, and we see by mass, iron 3 oxide is 69, almost 70% iron by mass. We could also do it for the other element, and really at this point you have 2 options. One option is you can just do it like you would normal. So the percent of oxygen would be the mass of the oxygen that's present. So in this formula, there's 3 oxygens at 16 grams per mole. And we would use the molar mass of the whole thing. So I'm going to steal their number there, which is 159.7. We'll hope that's right. We're going to times it by 100%. And if we do that, 3 times 16 divided by 159.7 times 100 gets us something like 30.06% oxygen. Now, that's obviously one way you could do it. The other way you could do it is because it's only iron and oxygen here. You know, 100% of it is made up of iron and oxygen, and you know that 69.94% is iron. So basically, you can subtract these two and get the percentage of oxygen in this case. So if you subtract 100% from 69.94, that obviously will give you this number here, and you could get it that way as well. So again, you could do the calculation there, or you could get it by subtracting from 100, since those are the only 2 elements involved. Question on that one there. So why don't you try this one here? In addition to the carbon, why don't you find the percentage of hydrogen and the percentage of oxygen that's in this compound here? And again, I'll give you some numbers in case you need. Carbon 12.01, hydrogen 1.008, nitrogen 1401, and oxygen 16. So we're looking for the percentage of carbon by mass, percentage of hydrogen and oxygen in that formula. Okay, so let's see how we're doing. So in order to really calculate the percent of each of these elements by mass, we do need to start with the molar mass of the entire thing. So that's a good place to start. So we have 17 carbons, each at 12.01. We then have 19 hydrogens, each at 1.008 from the periodic table. We also have one nitrogen at 1401. Now let's go on the other side here. And we have three oxygens at 16 grams per mole. So if we add all those guys together, so 17 times 12.01 plus 19 times 1.008 plus a 1401 and 3 times 16. Looks like it gets us something like 285.3 grams per mole would be our molar mass of the entire compound. Any questions up to that point there? So we're looking for the percentage of carbon. So we'll start there. So percentage of carbon, that means up on top, we want just the carbon part. So that's going to be 17 times 12.01 divided by the mass of the entire compound, which is 285.3 times 100%. And if we do that, 17 times 12.01 gives you like 204 divided by 285.3 times it by 100. And we'll call it 71.56% carbon. Any questions on that one? So we then want to do hydrogen perhaps next. So the percentage of hydrogen going to be done the same way. We're just going to take all the hydrogens, which in this case is 19 of them, times 1.008. Again, divided by the entire mass of the compound, times 100%. And that would get us for hydrogen, get about 19 up on top, divided by 285.3, times it by 100, 6.713%. Sorry, 6.713% hydrogen. And last, we could do it for the oxygens. So percent oxygen, we're going to take the number of oxygens that are on top, which are 3. Again, divided by the entire mass of the whole thing, 285.3. And again, times it by 100%. So 3 times 16 gets you about 48, divided by 285.3 and times it by 100. Looks like 1682%. That was oxygen. Question on how we got any of those numbers there. At this point, if we wanted nitrogen, we could do the same type of calculation. Take 1401 divided by 285.3 times it by 100. Or we could add up all three of these numbers and subtract 100 from it. It'll give us the same answer, so you could do it either way. Any questions on percent composition by mass? Okay, so what we're going to talk about next are some different types of formulas. The first one's an empirical formula and a molecular formula, and sort of the difference between them. And we oftentimes will be given a lot of things in sort of percent composition by mass when we do it. So let's first talk about what those things are. It's good they agree with us, I suppose. So the empirical formula is really the simplest whole number ratio of what's present. So it doesn't necessarily mean that it tells you exactly how many atoms of hydrogen are there or carbon are there, but it does give you sort of the simplest ratio of each of the elements to each other is the empirical formula. Empirical formulas are usually found a lot of times by percent composition of the compound, and usually you're given the percent composition. So a lot of times we do assume like 100% or 100 grams because that makes all the numbers sort of the same. Empirical formulas are often the formulas that we find sort of experimentally They're the ones that are sort of easier to find sort of experimentally because you can kind of figure out the simplest ratio that's coming together. So for example, CH is an empirical formula for, say, something like C6H6. So C6H6 was our molecular formula. And what a molecular formula is, the molecular formula actually tells you what is present. So the molecular formula tells you exactly how many atoms of each element are present. The empirical formula tells you that simple ratio of what's present. So C6H6 was our molecular formula, which tells us that in this guy, we have 6 carbons and 6 hydrogens. That is basically 6 carbons to 6 hydrogens. That is the same as a 1 carbon to 1 hydrogen relationship, which means the empirical formula here would be CH, would be our empirical formula, the simplest ratio that's present. If you had something like H2O2, which is hydrogen peroxide, that is 2 hydrogens for every 2 oxygens. You could reduce that down as the same as 1 hydrogen for every 1 oxygen in this case. And the empirical formula would be HO, as this would be our molecular formula. You know, if you had something like, say, C6H14, if you look at sort of the ratio that's present here in our molecular formula, that is 6 carbons to 14 hydrogens. In this particular case, you could reduce everybody down by 2. And if you did, that would be the same as 3 carbons for every 7 hydrogens, which would give us C3H7 would be our empirical formula in that particular case. So sometimes the molecular formula is written like this. It usually is, but you can sometimes put the empirical formula in parentheses and a little number on the outside to represent the molecular formula. But most of the time, people really do distribute that 6, for example, in this case, inside. Now, sometimes both the empirical formula and the molecular formula are the same. So, for example, if you take water, water is basically 2 hydrogens for every 1 oxygen that's present. And that's pretty much as far down as you could go. You can't reduce that down anymore to whole numbers. So H2O would be both the empirical formula and the molecular formula. So sometimes they are the same, sometimes they are different. And again, if you could reduce something down and give everybody still a whole number, that will get you your empirical formula. And again, your empirical formula is that simple ratio, and the molecular formula tells you exactly how many atoms are present. Question on that. So let's talk about how you actually go about calculating an empirical formula. And there are certain sort of steps to calculate an empirical formula. Here are sort of the basic steps. A lot of times you are given the percent composition by mass. So a lot of times you want to convert that percent into grams for each element. So if you're given the percent composition by mass, you want to convert it into grams. Second, you want to take those grams and convert them to moles, and that would be using the molar mass like we've been doing. Once you have everybody in moles, so for example, let's say I had 4 moles of A when I did it, and I also had 2 moles of B when I did that calculation. What you want to do is then divide by the smallest number of moles. So you want to divide by the smallest number of moles. So in this case, in my example, that would be, I would divide everybody by 2. When I do that, that would give me 2 for A, and that would give me 1 for B. And if you do this part and you actually do hit all whole numbers, then that would be your empirical formula. So my empirical formula, my made up one here, would be A to B. So again, if you hit all whole numbers when you do that, that would be your empirical formula. Now, if you divide, let's say we switch it around and we had say 5 moles of A and 2 moles of B. And we get to that part when we divide by the smallest, which would be 2. When I do this guy, I end up with 2.5 for A, and I end up with 1 for B. And that would give me an empirical formula A, 2.5, and B. If you remember, all these guys on the bottom do need to be whole numbers. You can't have like a half an atom or something like that. So in this particular case, we would have to clear that decimal. And it's too far to round. So unless that number is pretty much on the whole number, so like 0.99, 0.98, or just above the number, like 0.02, 0.01, somewhere in that range, where it's very, very close to the nearest whole number, you could round. But if it's something like 0.5, like we have here when you divide, or 0.33 is another common one that comes about, that's too far to round. So you need to find a way to clear it. So you just do kind of a trial by error. 2.5 times 1 gives me 2.5. 2.5 times 2 gives me 5. So that would be a whole number. So what that means is I would want to multiply my empirical formula by 2. Not just the A here, but everybody. And that would give me A5, B2 would be my correct empirical formula. So sometimes you get lucky when you divide by the smallest and you hit all whole numbers, which means that is your empirical formula. Sometimes you're not so lucky, don't hit the whole numbers, and you do need to kind of clear it. All right, so let us take a look at how we can apply sort of these steps here to this problem. So I just kind of maybe clear what's on here. All right. So in this case, we want to determine the empirical formula, and what they told us was the percent of carbon in this case is 83.65%. They also told us that this guy is made up of only carbon and hydrogen, so just those two elements. That means we can find the percentage of hydrogen because it's only made up of those two elements. The percentage of hydrogen should be 100%. Minus the percentage of carbon in this case, which would tell us that the percentage of hydrogen should be 100 minus 83.65 gives us 1635% hydrogen. So again, because those are the only two elements and they gave us basically the percentage of 1, we could subtract from 100 to get the percentage of the missing element. Any questions on that? So that's kind of step 1 here, leading into what we're going to do, which is now that we have the percentages of each of these guys, we could assume that we have 100 grams. The reason we assume we have 100 grams is when I convert my percentages into sort of a usable number, if I assume I have 100 grams of it, that means I would have 83.65 grams of carbon and 16.35 grams of hydrogen. It keeps the numbers the same. You could assume 200 grams if you want, but the numbers would change. So it's much easier just to assume that you have 100 grams of everything, and that will convert our percentages into grams. And what that means is we will have 83.65 grams of carbon, and we will have 16.35 grams of hydrogen. So again, we assume that 100 grams keeps the numbers the same. And now we could do the next step, which is we want to convert these grams into moles. So we're going to use the molar mass from the periodic table like we did in those previous calculations. So carbon is 12.01 grams per mole. Hydrogen from the periodic table, 1.008 grams per mole. So taking our grams and converting them into moles gives us, we'll call it 6.965 moles of carbon. And for our hydrogen, it is 16.22 moles of hydrogen. So that's sort of the second step here, which is convert everybody into moles. Any questions up to that point. At this point, what we want to do is we want to divide by the smallest number of moles. And what we're talking about is the moles of carbon and the moles of hydrogen. And in this case, it is the moles of carbon. So we would divide everybody by the moles of carbon, which is our smallest number in this particular case. And if we do that, we end up with obviously 1 here. When we divide those guys, we take our 16.22 divided by 6.965, gets us something like 2.33. Once we divide by the smallest, which is the third step, that would give us our empirical formula. And at this point, our empirical formula would be C1H2.33. Now, hopefully, when you look at this, you will recognize that this is not the proper empirical formula because it is not all whole numbers. Also, 2.33, that 0.33 is too far away to round to either 2 or 3. So we do need to clear that 2.33. And again, we could do that by just kind of trial and error. 2.33 times 1 is 2.33. If we take 2.33 times 2, that's going to get us, excuse me, we got there 4.66. Jeez, my calculator in my hand, huh? 2.33 times 3 will give us 6.99, and that is pretty close to 7 in that particular case. That means that we can multiply everybody there by 3 and achieve whole numbers. Again, not just this guy we need to multiply by, but we need to multiply this guy by it as well. And again, we're not multiplying by 7, we're multiplying by 3, which is the factor that we need. And that would give us C3, 1 times 3, H 6.99, which is close enough to round to 7. And this would be our empirical formula. Any questions on that one there? So those are sort of your basic steps: percentage to grams, grams to moles using the molar mass, divide by the smallest number of moles. Again, if you hit all whole numbers, you're good to go. If you don't, then obviously you need to do something like what we just did here to find a factor to multiply everybody by to get to that whole number. Any questions on that there? All right, we will stop there for now, and we'll pick back up there for lab at 12. So make sure you hit here if you haven't done so, and I'll see everybody in about 15 minutes.